Flutube. Get it straight.
Let's look at a linear momentum problem now, which is a little more complicated than the conservation of mass or continuity problems we've been doing. So let's look at a sluice gate where we have this water stopping behind a wall here and flowing out underneath the gate like so. So in this case, we have external forces balanced by the momentum that's coming in and going out of the system. So the difference in momentum across the system is balanced by the forces. Nothing is moving here except the water. The structure, the control volume is not moving. So the momentum must equal the external forces. So let's look at the external forces by making this kind of unique looking control volume, which is this strange looking box here that basically encompasses the water that is behind and going through the sluice gate. So we have a kind of different situation where we now have to track the pressure that's acting on one side, pressure that's acting on the other side become external forces on this control volume. And the third force we have is this resistance force by the gate. So there's pushing on the water's pushing on that gate as well, obviously. That's the purpose of the gate. So these three things make up the external forces acting in the x direction. There's not much going on in the y direction. All the motion here is horizontal. So we have pressure on one side, pressure on the other side, and the resistance. So the change of momentum, remember, we have this, remember before we just had this continuity term, but now we have a velocity term in front of it. So the continuity term also typically has a velocity going in, and so that we end up with the double velocity terms. We have the v times v dot n terms, and that's what tells us whether the momentum is a negative or positive. But it works out to be the same as for conservation of flow, where in is negative momentum and out is positive momentum. And you just really have to have a difference between what's going in and out so that you get that difference in momentum over the control volume unit. So in this case, we're always going to have this, important to remember, you're going to have a squared term for the velocity when you have the momentum. You have mass times velocity again times the cross-sectional area. So if we equate the forces to the change in momentum, we can rearrange to solve for our unknown, which in this case is the resistance on the wall. We also don't really know what V2 is, but we remember from Bernoulli way back in chapter 3 that we can figure this out. So you need to refresh yourselves on Bernoulli to see how we got that, but rest assured we can get V2 out of that. And then it's just a matter of doing the math here, plugging in the numbers, remembering what the width of the system is, and add it all up, and we'll come up with a total force on the gate of minus 9.5 kilonewtons per meter, which means that really the force should have been guessed this way, which makes sense. The water's pushing to the right, so the gate is pushing back to the left. The water force on the gate, if we wanted to know that, would be in the direction we assumed. So that's one of the first linear momentum problems. They're a little bit more difficult. It's important to remember in the external forces to consider these pressure terms on either side of the control volume. And then it's also key to all momentum problems to work with two velocities in order to get a velocity squared term in that momentum.